started with the foundations of convective heat transfer, the mathematical foundations of convective heat transfer. Now, the mathematical foundations of convective heat transfer strongly depend on fluid mechanics, and this is so because convection may be fundamentally perceived as advection assisted conduction. So, you have a situation where conduction is a must, but that is assisted by something which is advection or transport of heat by fluid flow. So, to get a physical picture of why fluid flow is important for heat transfer, let us consider a situation like this. Let us say that you have a solid boundary and fluid is coming from first stream with a velocity u infinity and temperature T infinity. Now, to write what is the heat transfer at the wall, we express it by this following boundary condition. We have discussed earlier that this boundary condition is valid for both steady state and unsteady state, and only important assumption is that radiation is neglected. Otherwise, there will be a radiation term along with it. Now, in convective heat transfer, we are mainly interested to find out what is H. If we know what is H, then we know what is the rate at which heat is being transferred at the wall, right? The question is, H will depend on what? What are the parameters on which H will depend? So, you can of course non-dimensionalize this equation and write, if you define a non-dimensional theta, non-dimensional temperature theta, and non-dimensional y by L, then you can write this equation So, what you get is a non-dimensional temperature gradient at the wall. Because this is non-dimensional, this is also a non-dimensional parameter which is known as Nusselt number. It is very important to understand that there is a fundamental difference between this Nusselt number and the Bio number that we have talked about in conduction heat transfer. We will come into that. Now, we will see what are the parameters on which we depend and we will bring a context by virtue of which we will understand that how fluid mechanics relates to heat transfer. So, my first question is, what is this K? Is this K of solid or K of fluid? Okay. This is my first question. Is this K of solid, or you have a solid wall and you have a fluid at the top of it? So, this is K of solid or K of fluid? So, sometimes as I often discuss that these days it is easier to get an answer if we pose it in multiple choice mode, right? Number 1 K of solid, number 2 K of fluid, number 3 either K of solid or K of fluid, number 4 none of the above we cannot say. So, 3 choices: K of solid, K of fluid, K of solid or K of fluid. Let us see. So, I am just enlarging the solid boundary, solid wall. This is the solid wall. Okay. Let us say that this temperature is T wall, which may be a function of x. X is this is x axis. T wall may itself be a function of x, may not be a function of x. So, if this is T wall, let us take an example that T wall is greater than T infinity. I mean, we can take two interesting examples. One is T wall greater than T infinity, another is T wall less than T infinity. T wall equal to T infinity is a redundant example, because then there is no temperature difference between the wall and the fluid. So, let us say this temperature is T1. If it is steady state, what will be the temperature profile between T1 and T wall? Linear temperature profile, right? So, let us draw it with some color. What will be the temperature profile in the fluid? In general, not linear. If it is a system where there is only conduction, that means the fluid is stagnant, then it may be possible that the temperature profile in the fluid is also linear, but in general it is not so. So, let us say that the temperature profile in the fluid is something like this. Okay. So, importantly, what is common at the interface? What is continuous at the interface between the solid and the fluid? Number 1, temperature is continuous, right? Temperature, because at a given point you cannot have two different temperatures, one in the fluid and one in the solid, right? So, at a given point you must have unique temperature. So, there must be continuity of temperature. And the second, the heat flux must be continuous. The rate at which heat is transferred from the solid to the fluid here is the same rate at which heat leaves to the fluid. The reason is that this is an interface. Interface does not have any thermal storage capacity. So, whatever heat comes at the interface, at the same rate it will leave. So, what is the rate at which heat is coming at the interface? Minus K right, S for solid. We will use S for solid and F for fluid. This is the rate at which this temperature profile, this is Ts, and this temperature profile is Ts. Okay. So this is equal to the heat flux at the wall. Wall means interface, not the bottom at this location. This is equal to H into T wall minus T infinity. This is nothing but the so called Newton's law of cooling. Okay. So this is always valid except when radiation is present, a radiation heat flux has to be added. Now, based on this, can you give an answer that whether it is K of solid or K of fluid? Yes? See, it all depends on whether you are using the temperature profile of the solid or temperature profile of the fluid. If here you are using temperature profile of the solid, then this will be K of solid. If here you are using temperature profile of fluid, it will be K of fluid. But in convective heat transfer, our interest of domain is the fluid domain. Therefore, we are interested to find out the temperature profile in the fluid and the temperature gradient in the fluid profile. So if we are interested to do that, that means this is K of fluid. But fundamentally, there is no restriction that it will be K of fluid. It depends on it is T of what. If it is T within the solid, then this is K of solid. If this is T within the fluid, it will be K of fluid. Okay. And you can see here that because in general Ks and Kf are different, therefore the slopes of these two lines are different. They are not, these two lines have same unique value at their points of intersection, but they do not have the same slope because Ks and Kf are in general different. Okay. So, important thing is that if this theta is theta of the fluid, now we write here theta of the fluid, then this is K of fluid. Right. So, non-dimensional temperature gradient of the temperature profile within the fluid is equal to HL by K of fluid. In the Bio number definition, the K was K of solid, and in the Nusselt number definition, K is K of fluid. Okay. So, typically we can say that Nusselt number is therefore a representation of non-dimensional temperature gradient in the fluid at the interface between the fluid and the solid. So, it will depend on what? Intuitively, the Nusselt number will be a function of these are the parameters, like out of these what are the fluid mechanics parameters? The fluid mechanics parameters are rho, u infinity, L and mu, and we will discuss about these parameters, why these parameters are important. And the non-fluid mechanics parameters are K, Cp and partly rho also. Rho partly contributes to the fluid dynamics parameters and partly contributes to the thermal parameters. So, the question is that why these parameters are important? These parameters are important because of the following reason. Let us take an example. Let me ask you a question. If u infinity is increased, do you expect a higher heat flux at the wall or lower heat flux at the wall? Question is, if you increase U infinity, do you expect a higher heat flux at the wall or lower heat flux at the wall? You expect a higher heat flux at the wall. The reason is like this. See what is happening with a higher U infinity, there is a higher rate at which heat is getting transferred by fluid flow. To compensate for that, to replenish that, more heat is to be supplied from the wall. So let us say that there is some person who is a voracious eater, who always eats, and after eating the person becomes more and more hungry, like a diabetic patient. So then, to make that person happy, you have to supply more food, otherwise that person will not feel happy. So this is something like this. So the fluid flow is carrying heat at a very fast rate. So to make up for that, more heat has to be supplied from the wall, right? So that is one of the very important parameters. Then the other parameter, L, is of course important because the entire characteristic length scale of the problem is governed by the length L. Mu and rho, the combination of mu and rho, what does it play a role? So it is essentially not mu or rho individually, but mu by rho, which is known as kinematic viscosity. Now question is, why mu by rho is important? Why not mu individually or why not rho individually? So what does mu do? If you think of this physical problem, let us draw a separate sketch here. Let us say this is the wall. The first molecules which are adhering to the wall will directly feel the effect of the wall. So if the molecules are significantly compact, then they are almost like trapped by the attractive interactions of the wall and they cannot escape from the wall. This in fluid mechanics, in classical fluid mechanics, is known as no-slip boundary condition. So that there is no relative tangential component of velocity between the fluid and the solid boundary. Of course, there are many situations in microfluidics and nanofluidics where this no-slip boundary condition is violated, but we will not discuss about that in the basic course. So let us say that there is a situation when the no-slip boundary condition is valid and the molecules are sticking to the wall. Now these molecules are sticking to the wall because they directly understand that there is a wall. Now consider the second layer of molecules on the top of these ones. This second layer of molecules, what happens to them? Does this second layer of molecule move with a velocity u infinity? No, it moves with a velocity much slower than u infinity, but not 0. So it moves with a velocity which is much slower than u infinity but faster than this. That means, why it is not moving at a velocity u infinity? Because it understands that there is a wall. How does it understand that there is a wall? It is not in direct contact with the wall. So how does it understand that there is a wall? There is a messenger in the fluid that propagates the message that yes, there is a momentum disturbance, and that messenger in the fluid is nothing but viscosity of the fluid. So viscosity of the fluid is physically a messenger for momentum disturbance. It gives a message that there is a momentum disturbance in the fluid. Now the fluid gets a message that there is a momentum disturbance, but the fluid has its own inertia. So even though there is a momentum disturbance, the fluid intends or tends to maintain its own momentum. By virtue of which property of the fluid? By virtue of inertia of the fluid. By virtue of inertia of the fluid tends to sustain its momentum, and inertia of the fluid is proportional to the mass, and mass is proportional to the density. So, mu is the tendency of the fluid to undergo a change in momentum or disturbance in momentum, and rho is the tendency to sustain the momentum. So, this is a relative ability of change of momentum with respect to the tendency to sustain its momentum, and that is why it is important as a basic feature. And you know, it is very interesting that there are different types of fluids which grossly vary in mu and rho, but in terms of the property mu by rho, there are many apparently different types of fluids which have close value of the kinematic viscosity. If you go to steel plants, you will find that there is flow of molten steel in steel plants. Now, to understand the fluid mechanics of molten steels, many times in the R&D divisions of steel plants, what they do is they make water models. That is, instead of studying the behavior of steel, they are studying the behavior of water in a transparent box. Now, the question is that why it is being done like that? Of course, the practical constraint is that molten metal flow at a very high temperature. It is very hazardous to deal with, it is very hazardous to handle. So, it is very difficult to do fluid mechanics experiments by visualizing that. Not only that, molten metals, most of the cases they are not transparent medium. So, you cannot visualize the flow. So, there are practical reasons, but the question is that when you cannot visualize molten metal, how can you replace water with molten steel? One of the basic reasons is that typically mu of steel is roughly 10 times mu of water, roughly one order, and rho of steel is also roughly one order more than that of water, right? So, mu by rho of steel is mu by rho of steel is roughly mu by rho of water. So, this is very remarkable behavior, that although density and viscosities of water and steel are grossly varying, but kinematic viscosity of water and kinematic viscosity of steel are roughly very similar. Now, that makes water models work, but only when heat transfer effect is not very important. When heat transfer effect is important, you also have to consider the thermal diffusivity, and thermal diffusivity of steel and water are grossly different. So, when heat transfer effects are very important, just by this similarity you cannot say that whatever will happen for molten steel will be the same with water, because the thermal diffusivity wise they are different. But purely from fluid mechanics considerations, this is the similarity. Now, we have to understand that what will be the role of this mu. That is, if you increase this mu, what will be the wall heat flux? Will it increase or decrease? See, what we are trying to do, we are trying to understand physically first the influence of fluid mechanics parameters on heat transfer, because that will give us a motivation of why should we study fluid flow equations in the context of heat transfer. In the context of fluid mechanics we study fluid flow equations, fine, but why in the context of heat transfer we should study fluid flow equations. So, U infinity role we have understood. So, now we have coupled these two and we are trying to see that what is the role of this mu. Now, if mu is high, what will happen? See, mu will dictate that how far from the wall you should go to attain u infinity. The distance from the wall that you go to attain close to u infinity, that is known as the boundary layer thickness, right. So, boundary layer thickness can be anything from very small to very large. So, the question is that when nu is increased, then what do you expect the boundary layer thickness to be, large or small? If nu is large, that means what is the, if nu is increased, then what is the distance up to which the wall effect is felt? The distance is more, right. So, more and more fluid understands the effect of the wall if the fluid has higher kinematic viscosity, because the momentum disturbance is very strong. So, if that means if nu is large, then the boundary layer thickness is large. If the boundary layer thickness is large, what is the velocity gradient within the boundary layer? If the boundary layer thickness is large, then the velocity gradient within the boundary layer for a given u infinity is small, right. Now, it can be shown that if we consider, so this is related to velocity gradient, we will discuss about velocity gradients later, but similar to the boundary layer within which the velocity gradient occurs, there is a boundary layer within which the temperature gradient also occurs, that is known as thermal boundary layer. So, in the thermal boundary layer, the temperature will change from T wall to T infinity. Let the thickness of the thermal boundary layer be delta T. So, delta by delta T what is delta related to? Delta is related to the kinematic viscosity of the fluid. Similarly, from analogy, can you say what is delta T related to? Thermal diffusivity of the fluid, right. Kinematic viscosity and thermal diffusivity are very similar parameters. Thermal diffusivity is what? Thermal diffusivity is K by rho Cp. K is just like mu by rho, mu is momentum disturbance and rho is momentum sustenance. Similarly, K by rho Cp, K is thermal disturbance due to conduction and rho Cp is the ability for thermal storage or thermal, that is thermal inertia. Okay. So, very similar. So, nu by alpha is related to delta by delta T, and this nu by alpha is a parameter known as Prandtl number. So, for a given alpha, if you have higher nu, you have higher delta, right. So, if you have higher delta, because the Prandtl number is a property of the fluid, you should also have higher delta T, because delta by delta T is fixed for a given fluid. So, if you have a higher value of delta T, then what will happen? If you have higher value of nu, you will have higher value of delta T. If you have higher value of delta T, then what is the temperature gradient within the thermal boundary layer? Is it more or less? Remember that we are essentially interested about the temperature gradient. So, what is roughly the temperature gradient within the thermal boundary layer? T infinity, T wall minus T infinity by delta T, roughly. If it was linear, this is just order of magnitude. Okay. So, this is roughly del T del Y at the wall, order of magnitude. Okay. So if you have higher delta T, you will have lower heat flux. Right? That means the Nusselt number will be low. Right? So you can see, we started with nu, we came with heat flux, something very non-intuitive, right? We started with a pure fluid mechanics parameter and we came up with a increase of nu will have a decrease of heat flux. That means decrease of nu will have an increase of heat flux. So decrease of nu and increase of u infinity and also increase of L are of same effect. So the net effect is of increase of u infinity L by nu. If you increase u infinity, the effect is like decrease of nu and increase of L, and this together as a combination is Reynolds number, that all of you know, right? So the Nusselt number for forced convection will be a function of Reynolds number and this parameter Prandtl number, right? I just tried to give you a pure physical argument without getting into any mathematics, just simple physical argument. But this kind of physical argument is very important because we should first develop a motivation of why are we interested to go through the fluid mechanics equations to understand convection. So here is the parameter which now is related to fluid mechanics. So this gives us a motivation of why should we study fluid dynamics for convective heat transfer. So when we say fluid dynamics, we have to keep in mind that fluid dynamics, to understand fluid dynamics, we need to understand basic equations of fluid mechanics. And what are the basic equations of fluid mechanics? The basic equations of fluid mechanics are the conservation equations, like conservation of mass, conservation of momentum, and in heat transfer you also have conservation of energy. So when we say conservation of energy in the context of heat transfer, we essentially talk about the conservation law dictated by the first law of thermodynamics. So energy where you have both heat and work involved. So we will start with conservation of mass, but before that we will try to recapitulate a general theorem which talks about conservation in fluid mechanics, and then we will apply that theorem to address the issues of conservation of mass, conservation of momentum, and then eventually conservation of energy, and that theorem is Reynolds transport theorem. Again, everything requires a motivation, right? We should understand that why are we interested about Reynolds transport theorem. I mean, as a teacher I believe that any teaching should not start with let us take a control volume, do this and do that, all these things are fine, but it is important to understand first that what you are trying to achieve with Reynolds transport theorem and why you are trying to do that. See, all the basic laws of mechanics, classical mechanics, are based on something, a concept which is control mass system, that is a system of particles of fixed mass and identity. If you think of Newton's laws of motion, the basic Newton's laws of motion, they also talk about some identified particles on which you apply the basic law. So you have a control mass system which in a mechanistic approach is also known as Lagrangian approach. That is, you track the motion of identified particles. The particles may be solid particles, fluid particles, whatever. On the other hand, in fluid mechanics, you do not commonly rely on Lagrangian approach. Why? Because fluid has numerous number of continuously deforming particles, and it is impossible to track the motion of individual particles just like that. You may track a motion of few identified particles, but the total description of motion of a fluid by identifying all the particles is difficult. So instead what you do? Instead you focus your attention on a specific location, as if you were sitting with a camera and focusing the camera at a particular location and seeing what change is taking place across that, what fluid is coming in and what fluid is going out. So that approach is known as Eulerian approach or control volume approach. So in fluid mechanics you are dealing with control volume approach, but the basic laws are all described on the basis of a control mass system. So you require a transformation from a control mass system approach to a control volume approach, so that equations of motion can be written in terms of a control volume approach, and that transformation from control mass approach to control volume approach is given by a theorem known as Reynolds transport theorem. That is why we need to study the Reynolds transport theorem. So let us say that we have a system this is basically a control mass system at time t. Let us say this blue colored outline is a system at time t plus delta t. Okay. This common region you can identify as a control volume, that is a fixed region on which you focus your attention over the time interval delta t in the limit as delta t tends to 0. So you can say that this is your control volume. Now this entire region can be divided into several parts. Let us say this is zone number 1, this is zone number 2 and this is zone number 3. Let us say that capital N is any extensive property of the fluid. So extensive property means a property which depends on the extent of the fluid or mass of the fluid. So N at time t is equal to N1 at time t plus N2 at time t, because at time t the system is 1 plus 2. Similarly, N at time t plus delta t this, okay, 3, this is 3. This is very straightforward. So what we are interested is to calculate what is dN dt of the system. So by definition, this is limit as delta t tends to 0, n t plus delta t minus nt divided by delta t. So, nt plus delta t, what is that? So, it has two parts, one is 2, another is 3, and nt it has also two parts, one is 2, another is 1. So, the two region is common for both, one at t plus delta t, another at t. So, we will isolate that, we will write limit as delta t tends to 0, n2 t plus delta t minus n2 t divided by delta t plus n3 at t plus delta t divided by delta t. What is that? That is the rate at which the property is flowing out of the control volume. Remember that as you are advecting in this way, this is acting like inflow and this is acting like outflow. So, this is plus rate of outflow minus rate of inflow of property. Of the property. Now, the next job is to express this mathematically, rate of outflow minus rate of inflow of property. So, let us make a sketch of the control volume. Let us say this is an outflow boundary. Let us say dA is an elemental area on the outflow boundary. Let us say that V is the velocity of flow at this outflow boundary. Okay. And small n is the property n per unit mass, capital N per unit mass. We also describe a unit vector normal to the surface. So, let us say that eta is a unit vector which is, so what is eta? Unit vector normal, outward normal. Now, can you tell what is the mass flow rate through this dA? What is the mass flow rate through this dA? What is the volume flow rate through this dA? Volume flow rate is the normal component of velocity times the area. So, what is the normal component of velocity? This is the normal component of velocity times the area is the volume flow rate. this times the density rho is the mass flow rate and small n is the property per unit mass. So, this times n is the total rate of the property flow across the outflow boundary. Okay. Let us think about an inflow boundary. Let us say this is an inflow boundary. What will be the difference between the inflow and the outflow boundary? The only difference is that when you calculate V dot eta, the dot product will be positive for outflow and negative for inflow. That you can see from this figure. The dot product of these two vectors is positive here, but the dot product of these two vectors is negative here. Right? So, if you write outflow minus inflow, you don't have to separately take two terms. If you now integrate it over the entire control surface, a positive dot product will mean the outflow part of the surface and negative dot product will mean the inflow part of the surface. Right? This CS is control surface, the surface that bounds the control volume. And the other term, which is this term, we can write this term as partial derivative of n with respect to time within the control volume. Why partial derivative? Because you are fixing your location 2 and at the same location you are finding the change of property with respect to time. So, change of property with respect to time at a fixed location. That is why partial derivative and not ordinary derivative. So, we can combine that and use in this expression to write dn dt of the system Now, what is capital N of the control volume? Let us say this is a small element dV, a volume element that we take. What is the mass of this element? Rho into dV. What is the property per unit mass? Small n. So, the total property is this into small n. So, this you can write there is one important point to note here is that what is this V? Let us say that this control volume is a tank. Let us say that there is a tank which is moving towards the right with a velocity of 1 meter per second. And let us say water is also moving towards the right at a velocity of 1 meter per second. There is a hole in the tank. Question is, what is the rate at which water is coming out of the tank? There is a tank in which there is a hole. The tank is moving towards the right with a velocity of 1 meter per second and water is also moving towards the right at a velocity of 1 meter per second. Then what is the rate at which the water is coming out of the tank? 0, right? Because water is moving at, the tank is moving at 1 meter per second, in the same direction water is also moving with 1 meter per second. So, there is no relative velocity of water with respect to the tank. So, the flow across a control surface depends on not the absolute velocity, but velocity of the fluid relative to the control volume. So, this V must be VR. velocity of fluid relative to the control volume, not the absolute velocity. So now see, we have been successful in deriving a general relationship where the rate of change with respect to a system, this is a Lagrangian parameter, is described in terms of rate of change with respect to a control volume, that is an Eulerian parameter, and this is known as Reynolds transport theorem. In the next 5 minutes or so, we will illustrate the use of Reynolds transport theorem for the law of conservation of mass. We will start with, as I told that in fluid mechanics, we are interested about some basic laws of conservation, and the most fundamental law of conservation is the conservation of mass. So we will start with that. The first example is conservation of mass. For conservation of mass, what is capital N? It is the total mass of the system. What is small n? 1, right? One small thing, so this is ddt, right? Because this is the total change, right? So just look at the previous step. So what is dm dt of the system? What is dm dt of a system? By definition, a control mass system has a fixed mass. So what is the rate of change of mass of a system? 0, right? So this is 0. So you have 0 is equal to now to simplify in the next step, there is an immediate tendency of taking this derivative inside the integral. Question is, can we do it or not? The answer is very straightforward. We cannot always do it, right? When we can do it? We can do it only when the volume of the control volume is not a function of time. Then you can put this time derivative outside and inside the integral as per your wish. Otherwise, you have to correct when you differentiate outside the integration and when you differentiate within the integration, they are not the same, and they have to be corrected by an additional term which is given by the Leibniz rule of differentiation under integral sign. So it is not that we can do it always. We can do this, we can put this inside, provided the volume of the control volume is not a function of time. So when the volume of the control volume is a function of time, let us say there is a balloon which is continuously expanding or contracting, whatever. So for solving a fluid mechanics problem in that, we cannot put this derivative within the integral. So we will make certain assumptions. One is non-deformable control volume, that means V is not a function of time, volume of the control volume. Second is stationary control volume. Stationary control volume means that the control volume is fixed. If the control volume is fixed, then relative velocity and absolute velocity are the same. Okay. So, under those conditions you can write finally, this is a volume integral. So, we can convert this into a volume integral by using the divergence theorem. So, we can write so if you have a vector function f dot say ds is equal to divergence of f dv, where the surface S over which the integral is made is a surface that completely bounds the control volume. By definition, the control surface is a surface that completely bounds the control volume. So, this is a very important prerequisite for the divergence theorem to be applied. So, when that is there, you can convert the area integral to volume integral. Why? What is the motivation? The motivation is that both of these terms are now having the volume integral. So, you can write integral of now let us look into a situation. You have integral of fx dx equal to 0. Does it necessarily mean that fx has to be 0? If it is a definite integral, not, right? For example, you may have a sinusoidal function, say y equal to sin x over a period, integrated over a period, the integral will be 0. That does not mean that sin x equal to 0 everywhere, right? But when this is true for any arbitrary choice of the domain, then the function must be 0, right? So, this is true for any arbitrary choice of the control volume. That is what is very important. Not just a specific choice, but for any arbitrary choice of the control volume, and that means that this must be equal to 0. This is nothing but the continuity equation in fluid mechanics. So, the continuity equation physically talks about conservation of mass. We will discuss in the next class some implications of the continuity equation, and then some special cases, what does it lead to for incompressible flow, maybe for steady flow, unsteady flow, these certain situations we will discuss, and then we will use the Reynolds transport theorem for a second example, which is conservation of momentum, and from that we will derive something which is known as the Navier-Stokes equation. So, that we will take up in the next lecture. Thank you.